Bonjour à tous. Okay, so in the third chapter, we have gaseous state in the fundamental toolkit of chemistry. So gaseous state is actually a standalone topic on its own because doing the calculations for gaseous particles actually takes a bit more effort than what we think. Okay, so in the syllabus, we assume that all of the gases are something what we know as ideal gases, which differs from something called real gases. So what are ideal gases? Right, so ideal gases follow a few assumptions. The first is that the volume occupied by the gas particles is negligible relative to the volume of the container. So the importance here is that relative to the volume of the container. Okay. Next is that the intermolecular forces of attraction between the gaseous particles are negligible. So if you recall from chemical bonding, we have had to compare the intermolecular forces of attraction between simple covalent structures, and gaseous molecules have intermolecular forces of attraction. So think in terms of those things. Next is that the collisions between the gas particles and the walls of the container are perfectly elastic. So perfectly elastic means that there is no loss of energy. Okay, so when it's flying, it has kinetic energy, right? So when it bounces off, no kinetic energy is lost. And the fourth and the most obvious one is that the gas particles are in constant random motion. So we should already know this from kinetic particle theory, right? Okay, so why we need to know these assumptions is because we need to use these assumptions to, say, explain any deviations that we observe from experimental results, or just to use it for explanations, basically. Okay, so there are two main conditions that approach ideality, which means that under these two conditions, a gas is most likely to behave as a ideal gas. So these two conditions are low pressure and high temperature, or what I like to call an ideal lifestyle is to have low stress and have a lit life. Okay, so low stress, lit life, low pressure, high temperature. Okay, so low pressure is, why is low pressure so? Is because at low pressure, you think about it, at low pressure, the gas particles are, they're not subjected to any pressure, right? Okay, low pressure, not no pressure, low pressure, because it's not possible to have no pressure. All right, so low pressure just means that the particles can fly around as much as they want, and they are far away from each other, right? So they are far away from each other, then this supports the first assumption that the volume occupied by the gas particles is negligible because they're so far apart that they occupy the entire thing. And then because they're so far apart, the intermolecular forces of attraction are now negligible, right? And this supports the second assumption. So based on this, low pressure is one of the conditions whereby a gas approaches an ideal gas. Next is high temperature. So at higher temperature, you supply more thermal energy, right? And then this thermal energy is converted into kinetic energy. So we know that at higher temperatures, gas particles move much faster. So when they move much faster, they are able to, this amount of energy is able to overcome the intermolecular forces of attraction, and therefore making the intermolecular forces of attraction negligible. And this supports the second assumption. So in any case, during the examination, when you are explaining anything that has to do with ideal gases, always come back to the assumptions of the ideal gas and use them to support your argument. Okay, so from here, we have the ideal gas law. The ideal gas law is PV equals to nRT. Take note of the units because questions don't always give you in the units that are supposed to be inside this equation. So always remember the units and do your unit conversion. So pressure is in pascals, volume is in meter cube. 1 meter cube if you don't know how to do the conversion. So 1 cm equal, okay, so 1 meter equals to 100 cm, right? Let me erase that. So 1 meter equals to 100 cm. So 1 meter cube equals to 100 cube cm cube, which is equals to 1 times 10 to the power of 6 cm cube. So from cm cube to meter cube, so from cm cube to meter cube, you need to divide by 10 to the power of 6. And then from dm cube, so 1000 dm cube equals to 1 meter cube. Okay, so when you want to go from dm cube to meter cube, you just divide by 1000. So that's how you do the conversion. Okay, N is the amount or the number of moles. R is the ideal gas constant, which is in your data booklet, the first page, I guess. And T is temperature in Kelvin. In Kelvin, so degrees Celsius. So to convert degrees Celsius to Kelvin, you just plus 273. Okay. The next law is Dalton's law of partial pressures. So the partial pressure of a particular gas in a mixture is the mole fraction or the ratio of the amount inside the entire mixture multiplied by the total pressure. Okay, so if you have like 1 mole of nitrogen in a mixture of 5 moles, that is 5, that has a total pressure of 5 pascals, right? So if you have 1 mole of A inside a total mixture of 5 moles of total pressure 5 pascals, then the partial pressure of A equals to 1 over 5 times 5, which is 1 pascal. Okay, so then let's move on to some graph sketching. So there's not much to cover in this topic, but some of the famous questions that like to come out, this especially in MCQ, is how do the graphs look like? So you can always think about how the graphs look like based on the formula PV equals to nRT, and then you just use it to your advantage, right? So first, this graph here is a horizontal line. So how horizontal lines are is when you have something like y equals to 5 or something, right? And then this is known as a hyperbola. A hyperbola is when you have something that's y equals to 1 over x. A straight line is when a straight line that passes through the origin is when you have something like y equals to 2x, right? And then a vertical line is when you have something like x equals to 5. So just use all of these relationships to draw the graphs. So something like PV against P, right? So PV equals to nRT, right? So PV is the y-axis, and then P is the x-axis. So where is x, right? There's no x, so y equals to nRT. So PV equals to nRT for this graph. P is the y, V is the x, so P equals to nRT over V. So as you can see, this is like a y equals to 1 over x graph, right? Okay, and then this PV equals to nRT. So same, P equals to nRT over V. But because now the x-axis is 1 over V, so this is like linear law, right? nRT 1 over V. So now this is y equals to nRT times x. So you get a straight line, okay, a straight line that passes through the origin, right? With a gradient of nRT. So you can work out the rest yourself. Yeah. So let's move on to deviations from ideal. So this is what we call a real gas, right? A real gas. So when we want to explain deviations, right, like from this graph here, we just use the assumptions to explain the deviations because we need to account for deviations by looking at the assumptions. So in this case, I give you an example of methane and ammonia, right? So we look from the graph here that NH3 actually deviates more than methane, right? So we can tell the deviation by how much it deviates from the nRT line, right? Because if you drew based on the ideal gas law, you will get a horizontal line of nRT. But we see that the graph is actually like this. Why? Okay, so first let me explain the shape. So as the pressure increases, the gas particles become closer together. So when they become even closer together, the intermolecular forces of attraction become more significant, right? So when it becomes more significant, then it will go down, right? Because now the intermolecular forces decrease the force, the net force on the wall. So therefore the pressure decreases. And then right, so as you can see, this going down, right? Why is it that CH4 goes down less than ammonia? So think back to intermolecular forces of attraction. Ammonia contains what? Hydrogen bonding, right? But methane is a non-polar compound, and non-polar compounds have only dispersion forces, which is the weakest out of all of them, right? So the weaker the intermolecular force of attraction, the smaller the deviation, and that's how you interpret this graph here. Therefore, as I have written over here, since ammonia experiences stronger intermolecular forces of attraction, it has less negligible intermolecular forces of attraction, and therefore it deviates more. So another way the question can ask you is they can just ask you to draw this graph, and then it's always a curve, okay, like this. So that's the end of gaseous state. It's actually quite a short topic because most of the time you will be doing calculations and it will link to other topics. So make sure you master calculations in this, and yeah, consider getting this as part of a set in the fundamental toolkit of chemistry. And as well, you can sign up for a membership, or you can always just support me on the coffee shop. So see you in another content summary video. Okay, goodbye.